Hello there, Mr. Sutton here with the BC Calculus 8.3 Extra Practice Number 1 solutions on vectors. On this problem, we're given the parametric equations for the position of some particle, and we want the acceleration vector at time 1. Well, to do this, we're going to need to take two derivatives because that's going to give us velocity and then acceleration. So let's start with the velocity vector. So taking the derivative of each of these, my x prime is going to be 4 plus 2t. For y prime, this is just going to be, let's see here, this is really 3t plus 1 to the negative 1. So this is going to be negative 3t plus 1 to the negative 2 if I take that derivative. But then I have the chain function going on because I have an inner function of 3t plus 1. So I have to multiply by 3, the derivative of all that. All right, moving on now to take another derivative to get to acceleration. So derivative of 4 plus 2t is just going to be 2. And for this next expression, I'm going to have negative 2 times negative 1 times 3. So that's 6 outside. But then I have another chain rule. I have to multiply by the tail of 3 off of that stuff. So that's 18 3t plus 1 to the negative third when all is said and done. So to make the next step easier, I'm going to clean this up a little bit. And I'm going to write this as, let's see here, 18 over 3t plus 1 to the positive third power. There we go. All right, so now I have to plug in 1 for all of this. So here's what that looks like. 2 is just going to be 2. This stuff, we've got a 1 plugged in downstairs. So that's going to be, let's see, 3 plus 1 is 4. If we raise that to the third power, that's 64. 18 over 64 can be reduced by 2. To be 9 over 32. So we have 2 comma 9 over 32 for the acceleration vector, which is going to give us choice B. For this problem, we have a particle moving along this parabola, and we have a constant speed of 2 radical 10 units per second. They're telling us dx over dt is positive. They want the value of dy over dt at the point 2 comma 2. All right, well, the key to unlocking all of this is they told us we had a constant speed of 2 radical 10. So I'm going to start by setting up an equation with speed in it. Speed in general, that's going to be the square root of dx over dt squared plus dy over dt squared. And this speed here should equal 2 radical 10 in this problem. So at some point, we have to solve for dy over dt. That's going to be tough, though, because we don't have anything for dx over dt yet, other than the fact that it's positive. So to get a little bit more information, we're going to go back to this parabola that they told us our particle is moving along, and we're going to differentiate this with respect to time, so implicitly differentiate it, kind of like a related rates problem. So this is going to be dy over dt, and then x squared becomes 2x dx over dt, minus this is going to be another dx over dt. Now, my goal in everything I'm doing over here, at some point, I want to get an equation where I can substitute something with a dy over dt for a dx over dt. Because I want to, just thinking ahead here, substitute for this dx over dt in our original speed equation. All right, so one thing that'll help us out here, they told us we were at the point 2 comma 2. So if we're at 2 comma 2, that means that I can replace this x in here with 2. So I've got dy over dt equals 2 times 2 dx over dt minus dx over dt. So this is really 4 dx over dt minus 1 dx over dt. That's 3 dx over dt. dy equals all that stuff, but we want to substitute for dx over dt itself. So I'm going to isolate dx over dt by dividing both sides by 3. So then that means that 1/3 dy over dt can be substituted for dx over dt. All right, I finally have something I can replace this dx over dt with that I don't want. So over here now, I'm going to replace this dx over dt with 1/3 dy over dt. I'm not saying it's going to be pretty, but it's going to get us where we need to go. So here's my equation now with 1/3 dy over dt plugged in there. And although, again, it's not pretty, I only have one unknown, or one type of unknown that I'm solving for, these dy over dt's. So the rest of this is just going to be some algebra. All right, so next step on this then, to get to any of these, I need to get rid of these square roots, so I'm going to square both sides of the equation. On the left side, and by the way, when I'm doing this, I'm also going to square this 1/3 dy over dt. So on the left side, I'm going to have 1/9 dy over dt plus dy over dt squared. And this dy over dt in here actually is still going to be squared. So no square root, 1/9 dy over dt squared plus another one of those equals, now I have to be careful, I'm going to be squaring the 2 and the 10, so that's 4 times 10, or 40 on that side. Next, I'm going to combine like terms on the left side. So I've got 1/9 of these, and this 1 over here, this is really 9/9 that I'm adding. So I've got 10 over 9 dy over dt squared. Let me get rid of this fraction now. I'm going to multiply both sides by 9 over 10. So 40 times 9 over 10, let's see, 40 divided by 10 is 4, times 9 is 36. So I have dy over dt squared equals 36. Now we're going to take the square root of both sides. So I've got 6 when I do that. And let's see here, that's going to give me answer choice D. On this problem, we have a particle whose coordinates are given by these parametric equations, and we want the acceleration vector at time 1. So I need to take 2 derivatives of these in component form. Setting up my velocity component, I've got, let's see here, x prime, which is going to be 2t, comma, now the y prime here, that's going to be 4t cubed minus 6t squared. So that's velocity. Next, to get acceleration, I have to take one more derivative. So this 2t is going to become a 2. And this other expression, this is going to be 12t squared minus 12t. At this point, I've got an expression for acceleration. I just need to plug 1 into all of this. The 2 obviously is just going to be a 2, but we have 1 plugged into this other expression. So this is 12 minus 12, which is just 0. So that ends up giving us answer choice D. For this one, we have a particle moving so that its position is given by these parametric equations. We want the speed of the particle at time 3. So to get that, I need the square root of, we need x prime of 3 squared plus y prime of 3 squared. Basically, just taking the Pythagorization of the velocity components. So this is the setup we need. Now, in order to do this on the calculator, I actually don't need to even figure out what x prime and y prime look like algebraically, although it wouldn't be tough, because I'm just taking the derivative at a single point. Calculator can do that. So let's go ahead and do that now. So I've got my x plugged in for the y1, and y of t, that's my y2. Going out to the main screen now, I need the square root of, and now I'm going to need the derivative of x at 3, square that, plus derivative of y at 3. Let me do that off camera here. So here's what it looks like for x prime of 3 squared. So math 8, alpha trace y1, x equals 3, put a little square outside. And let me do the same thing now for the y prime. There we are. There's the setup for y prime. Enter. About 6.884. So choice C. For this problem, we have a particle with a velocity vector given by these components here, t squared and 5t. We want the acceleration vector at time 3. So since we've already got velocity, we just need to take the derivative of that and plug in 3. So for our acceleration general vector, we've got 2t, comma 5. Plugging in 3 now, that's going to be 2 times 3, comma 5, or 6, comma 5. Choice B. On this problem, we've got an object moving given the parametric equations x of t and y of t. We want the speed at time 1. So I basically need to do x prime of 1 squared plus y prime of 1 squared and square root all of that like so. That's my speed, just Pythagorizing our velocity components. So let me go ahead and plug that in the calculator. So here I've got x of t plugged in as y1, y of t as y2. And let me quit to the main screen here. So I'm going to need square root, and now I need to take the derivative of y1 and y2 at 1. So let me go ahead and do that. So here's the setup for x prime of 1 squared, derivative with respect to x, y1, x equals 1 squared. And let me now add in pretty much the same thing for y prime. There we go. There's y prime. Again, I stored that in y2 and press enter. About 1.319. So that's choice B. For this problem, we have a particle moving with a velocity vector given as follows here, this v of t. If the particle is at point 1, 1/2 at time 0, how far is our particle from the origin at time 1? So we basically have to find the x and the y value at time 1. And then if you want to know how far you are from the origin, you can just use the Pythagorean theorem on the x and the y value that you've got. So let's figure out x of 1 and y of 1. To do that, I'm going to need to use the fundamental theorem. So I've got x of 1 equals my initial x value of 1 plus an integral from, let's see, we're going from 0 to 1 of, and now I need x prime of t dt. So that's 3 dt then that I'm actually plugging in. Let me do that on the calculator. Actually, I don't really need to do that on the calculator. This is just a rectangle that I'm adding in here from 0 to 1, and we have a height of 3. So this is just 1 plus 3, which is 4. All right, now for the other one, we've got y of 1. That's going to be the initial value of 1/2 plus an integral from 0 to 1 of 2 to the negative t squared dt, or y prime of that. Let's plug that in the calculator. So here's what this looks like on the calculator. I would normally store this as y1 and use y1 in here, but we're only using it this one time, so whatever. Enter. That's about 1.310. And I'm actually going to store that as p because I'm going to have to use it in a second, and I want to use the exact value if I can. So again, that's about 1.310. So now to find the distance from the origin, I need to take the Pythagorean theorem of these two coordinates, so square root of 4 squared plus p squared, and let me do that on the calculator now. So first, back on my calculator, let me store that answer that I just got as p. There we go, or whatever letter you want. Now we have the square root of 4 squared, which we could have just written 16, plus, let's see, alpha p, come on. There we go, and let's square that. Enter. And that's about 4.209. So that's answer choice C. For this calculator-based free response, we have velocity vector of a particle given as follows here, dx over dt, and here's your y prime, dy over dt. And that applies between 0 and 1.5. Now, since this is a calculator problem, I'm immediately going to enter these in my y equals. There we go, both entered in there because I never want to have to enter these again on the calculator. All right, so for part A, and they told us the position of the particle at time 0 was -2, 3. That'll be useful later on. But for part A, just between 0 and 1.5, we want all t values where the line tangent to the path is vertical. Well, if our tangent line to the path is vertical, that means there is 0 horizontal movement going on at that time. So that means we want our x prime here, which tells us the horizontal movement, to have a value of 0. So we're going to solve for some t values where this is true, between 0 and 1.5. And once we find those, we're also going to plug them into y prime just to make sure that there actually is some vertical movement. So that we don't want the y prime to be 0, just x prime. All right, so let's do this on the calculator. So back in my y equals, I only want to graph x prime and see where that crosses the x-axis. So let me go ahead and deselect this y2 here where I have my y prime stored. And now let me do window, and we're going to go from 0 to 1.5 because that's what they told us we're looking in. And then let me do zoom 0 and see what this looks like. And then we'll find the zeros. All right, so here is our x prime, this 14 cosine of t squared function. And it looks like it crosses twice right down here. So let's find those intersection points. And when I do, I'm going to store them as A and B. So let me do second trace, option 2 for zeros. and it's going to be kind of close in here, but I'll eyeball it as best I can. So we'll do enter once, and it looks like I'm below the x-axis there, so enter again, enter a third time for that 0, and that first 0 is about 1.1447. So there's that one. I'm going to store that as A back on my calculator. So let me quit out of the graph, and let me do sto and then alpha A. Now I can come back and use that whenever I need to. The reason I'm storing it is because I know I'm going to be plugging this into y prime in a minute, so I might as well store it, and if it's not useful any other time, I'm okay with that. All right, going back to my graph now. So second trace again. Let me find the other 0. I'm already below the x-axis, so let me press enter. And then let me move to the other side of the x-axis and press enter again. One more time. And our second 0 is at about 1.2533. I will store that as B. So going back here, exit out of there. And let's see, we're going to store this as alpha B. Okay. So at this point, I need to plug both of these values into y prime here, which I've stored in my y2, to see whether or not they equal 0. So let me do alpha trace and pull up y2. That's my y prime again. I'm going to plug in, let's see, alpha A there, that first intersection I found, and that comes out to about 2.9326 and some change. The important point here is that it's not 0. That means that we do have some vertical movement, so we do have a vertical tangent line at t equals A, which we already spelled out what that is. So this is another reason I called it A. Now I don't have to rewrite that number. All right, let me do the same thing for my B time here. And just to save a little bit of time, I can yank my input from before, y2. And now I'm just going to go inside there, and I'm going to do alpha B instead of alpha A. Enter, and that comes out to 3, exactly 3. Interesting. Well, again, that's not 0, so we have a vertical tangent line then at time B. For this problem, we want to write an equation for the line tangent to the path of our particle at time 1. So to get a tangent line, we need 3 parts. We need the x value, the y value, and the slope. Let's get the x and the y first. Now to do this, they gave us an initial position, and they gave us the derivatives of x and y. So we're going to use fundamental theorem to individually get x and y. For my x value, I need to take my initial position of -2 for x, and I have to add the integral of x prime from, let's see, 0 to 1. So integral from 0 to 1, x prime of t dt. And let me do that on the calculator. So here's what that looks like on the calculator. -2 plus integral from 0 to 1 of y1 dx, because again, y1 is where we stored this x prime. See, it's already coming in handy that we stored it in there. Press enter. That's about 9.315. I just need 3 decimals of accuracy here. Let's do the same thing to find y of 1 now. So we have our initial position of 3, and to that we're adding an integral, again from 0 to 1, of y prime of t dt this time around. Let me go for the calculator on this one. And I'm actually just going to yank my input from before because it's mostly got what I need. Some things I do need to change, though, if I go back here. So I don't want 2. I want 3 as my starting point. And then going in here, I don't want y1. I want, let's see, alpha trace. We want y2 because that's where I stored my y prime. Otherwise, everything is exactly the same. Press enter, about 4.621. So there is y of 1. Now I need the slope at t time equals 1. All right, well, to get slope in general for parametrics, we've got y prime of the number over x prime of the number. So our dy over dx evaluated at 1 is going to be y prime of 1 over x prime of 1. Let me put that on the calculator. And here's what that looks like. Fancy fraction, y2 of 1, because that's y prime of 1, over y1 of 1. Enter. Gives us about 0.863. So I've got everything I need. I'm just going to put this in point slope form now. So I have y minus the y value about 4.621 equals my slope of 0.863 times x minus my x value of 9.315. And there's my tangent line. For this part, they want the speed of our particle at time 1. So for this, I just need to take the components of velocity and put them in the Pythagorean theorem. So I'm going to have x prime of 1 squared plus y prime of 1 squared, square rooting all that. And conveniently, I already have these two functions here entered as y1 and y2 in my calculator. So let me just go straight there and take care of that. So here's the setup on the calculator. I've got the square root, and again, x prime was y1, so we have y1 of 1, and we're squaring that, along with y2 of 1 squared. Enter. About 4.105. And there's no units, so we don't have to give them any units. For this last part, they want the acceleration vector at time 1. So for that, I'm going to need x double prime of 1 and y double prime of 1. Now, the good news about this is that since I'm just taking the derivative of these functions that we've already defined at a single spot, I don't actually have to spell out what x double prime and y double prime look like algebraically. I just need to actually take their derivatives at 1 on the calculator. So let me do that now. So here is the derivative of x prime at 1 on the calculator. And this is actually x double prime of 1 then. Enter. It's about negative 28.425. So we'll put that as x double prime of 1 in our acceleration vector. And then going back now, I need y double prime of 1. So let me just yank my input from before, because that's almost what I need. But now instead of y1, I'm going to do alpha trace and do y2, because that's where I stored my y prime. So taking the derivative of that's going to give me y double prime at 1. Let's press enter. That's about 2.161. So there's our acceleration vector.